In this relatively short video, I'd like to describe a method of measuring the misfit between our simple or linear regression and our XY data. And the quantity I'm going to describe how to compute is the square root of the mean square error. Or in other words, the RMS error. And the RMS error, we'll refer to that as capital E RMS, is exactly how it's described in the above sentence. It's the square root of the mean square error. So our total square error was the sum of all our errors squared, and we divide by n to get the mean, and then so this is and then we take the square root of that, as I said before. And first of all, let's talk about how to compute this in a matrix form. So each error, that's each error, it's the error at each point of x is equal to our best fit equation, which is a1 plus a2 times xi minus our reference value of x minus our observed value of y. Remember, xi and yi are observed values. So this is the ith error of our equation. And we can write this equation as a vector equation. So what this is really describing is a vector of errors, E1, E2, all the way to En. So that's a vector on the left-hand side. We'll refer to that vector as E with a bar over it. And the right-hand side is a matrix equation with the matrix 1 on the left column and x1 minus x0 on the right column, and so on. And then we have to multiply by our vector of coefficients, which is just 2 rows in this case. We have 2 coefficients for our linear regression. And then we subtract our vector of y measurements. So if we were to continue to write this in matrix form, actually let me do that below this. Again, we have a vector E on the left-hand side. That's our error vector. And we can write this matrix in the form of, well, we could describe it as any letter, but we'll call it A. And this matrix we'll call that X. And let's just refer to this Y matrix as B. So we've found the coefficients that minimize the difference between AX and B. So with those vectors and matrices defined, we can calculate ERMS as the transpose of our error vector times our error vector. That gives the sum of square errors. And we divide that by n, and we take the square root of all that. And just to illustrate why E transpose E is equal to this, gives this sum, is you can see that E transpose is E1, E2, all the way out to En. And then we're multiplying it by E, which is a column vector, E1, E2, And by the matrix multiplication, we would multiply E1 times E1 and add that to the product of E2 times E2 and so on. And that gives, again, our sum of square errors. So this is ERMS. And so what we can do is we build A and X and B. And for example, in MATLAB, once we build those vectors, we would say vector E is equal to A and a matrix multiplication of X minus B, and ERMS is equal to the square root, and I'm just writing it how you would in MATLAB, and you would say E transpose times, again, a matrix multiplication times E, and in MATLAB you don't write a T, it's a prime, E prime, and then you would divide by N, and then that's all in the square root. So if our fit is good, our ERMS is relatively small. And so you can see that ERMS is a very convenient way to quantify how well our linear regression actually fits X versus Y of our data. So that will conclude this short video on how to quantify the RMS error for linear regression.